Okay, so now we're going to talk about normalizing orthogonality and superposition in this video. So normalizing the wave function. One of Born's postulates was that if you were to sum up the probability density dx equals, so if you sum it all up, you should have equal to 1, which means you have 100% probability of finding the electron, where psi is the solution to the Schrodinger equation. And I should also add, a lot of times you'll see it look like this, psi star psi dx. That's because psi is typically both real and it has a complex number in it sometimes, but psi squared needs to be real. So psi star psi means that you take, so if psi is equal to e to the I x, psi star equals e to the minus ix. Anytime you see a star, that means you have what's called the complex conjugate. And every time you see a complex number I, where I equals square root of -1, every time you see an I, you make it a negative. So this would be e to the I, or e to the minus ix times e to the ix. Okay. But we don't really use complex numbers in this class because we're not doing time dependent or time. Yeah, we're not doing time dependent. We are using the time independent Schrodinger equation. So psi star psi for us most of the time is just equal to psi squared because our psi's are real. Okay. So what we're going to do is we are going to have, so we're going to normalize our psi, which means that we are going to force this statement to be true. What does that mean? So let's, let me just show you via an example and then we'll talk about it. So I want to, so the goal is to normalize psi, which equals e to the x. Okay, so that means, so psi squared dx equals 1. But the problem is if I were to take, how do I know that this is true? Well, I'm going to force a constant. So I'm going to include a normalization constant, a, such that psi equals a e to the x. Go team. So then if I then say, okay, well, psi squared dx is equal to 1 is actually saying that a squared e to the 2x dx is equal to 1 when I integrate, and I'm going to give my limits of integration from 0 to some value little a. So then what's going to happen is I'm going to say, well, a squared, that's just a constant. I can take it out of the integrand because it doesn't depend on x. A squared integral 0 to a e to the 2x dx, that equals 1. Okay, so this is a true statement if and only if a equals something specific. So we're going to solve for what a is. So a squared equals 1, whoops. So a squared 1/2 e to the 2x from 0 to a. Sorry, to go and do the integral. So the integral of e to the 2x dx is going to be e to the x, and as long as you have, so if I take the derivative dx here, I have e to the 2x multiplied by 2. So what I want to do is take the antiderivative. So this means that if I'm going to take the antiderivative, I want to have a 1/2 in front, and then I'm going to get back again what's in the integrand. Okay, sorry, I was standing in front of that. And so here then I get a squared times 1/2 e to the 2x evaluated from 0 to a, which means I've got a squared times 1/2 e to the 2a minus, whoops, 1/2 e to the 2 times 0. Okay, so if I solve for this, this gives me a squared over 2. I'm going to take both of the 2's out, multiplied by e to the 2a minus 1, because this becomes e to the 2 times 0. That's just a 1. So e to the 0th power is 1, and that's multiplied by 1/2. So I have e to the 2a minus 1. And so then this whole thing equals 1. And so what I get then is solve for a, and I'll come up here. So A equals 2 over, so there's a 2 right down here, divided by e to the 2a minus 1. Okay, and all of that to the 1/2. You might be like, Allison, you totally lost me. What the hell are you doing? And that's okay. We are among friends. All right, so I don't know that my wave function is normalized, which means if my wave function looks something like this, who cares? It looks like that. Then I've got from 0 to a, I don't know if this will give me, if I were to take psi squared of this function and integrate it from this spot to this spot, am I guaranteed 100%? Am I guaranteed to equal 1? Well, I can force a constant that will guarantee that I have this equation normalized. And so what I do is I project, or I propose that I have some normalization constant a. And so I'm like, okay, so that means that psi squared dx is actually equal to this quantity squared. So I've got a squared e to the 2x, and that's 2 is because this is psi squared. And so what I'm going to do is I'm going to solve for this normalization constant, set this whole function equal to 1, solve for what a has to be in order for this to be true, as in for this whole thing to equal 1, a has to equal something. Cool. If I set this equal to 2, this would be different because a would be whatever is necessary to equal 2. If this was set equal to 4.73, a would be different because a, under the conditions of this is equal to 4.73, would be something else normalized to 4.73. Okay, we're normalizing to 1. So a now becomes my normalization constant, which means if I stick this in front of, so if psi equals 2 over e to the 2a minus 1, 1/2 e to the x, if I were to integrate that from 0 to a, my answer would be 1. Go team. Okay, that's called normalizing, and you always need to include a normalization constant with your wave function to guarantee that you satisfy Born's postulates. All right, you're going to do some examples of that, and we'll do some examples in class. Okay. Next is orthogonality. So if you have two wave functions, you have wave function 1 and wave function 2. They must be orthogonal to each other. Okay? And so the reason for that is if you have psi 1 times psi 2, that's going to equal 0 if psi 1 and psi 2 are orthogonal. Okay, this is very important with bonding. And in our initial systems, the particle in a box, the rigid rotor, we're not going to have orthogonality as much, but when we get into chemical bonding, very important. Okay, so psi 1 must be orthogonal to psi 2 such that if this is true, psi 1 times psi 2 integral, dx equals 0. On many of your homeworks, y'all are going to forget this dx, and I'm going to get all mad because this is true. If you forget the dx, that makes no sense. You need to have the dx. This is important. Okay, one thing I want you to think about with orthogonality are vectors. So if two vectors are orthogonal to one another, so here's vector 1. How do I do this? So this is vector 1. This is vector 2. These are orthogonal to each other, also known as perpendicular, but it's perpendicular in n-dimensional space. So if you think of, so if this is A and this is B, A is orthogonal to B, okay? So for wave functions, from Stefan's class, you know that wave function overlap is important in molecular orbital theory. If I have wave function 1 and wave function 2, and there's no overlap whatsoever, I don't have any bonding occur, or I don't have any superposition, or not really superposition, or a combination of the two wave functions. And so it's important to identify when they're orthogonal. If I have, however, A looks like this, and B looks like this, then there's a projection of A onto B, which is C, okay? So A projecting onto B yields C. And actually, I guess that wouldn't really necessarily be a vector, it'd just be a quantity. And so that projection is going to be relevant for us soon when we get into bonding, okay? So the other thing is if all the wave functions are orthogonal and normalized. So if A is orthogonal to B, this picture. A is orthogonal to B, and both A and B are normalized. You have what are called orthonormal sets. Okay, cool. That's orthogonality. Okay, now we're on to superposition. So for the so a superposition involves the fact that wave function is a combination of eigenfunctions for an observable. So for the example of momentum, okay, so for the example of momentum, I have the wave function of the momentum is equal to the sum of wave function 1 plus wave function 2 plus wave function 3 and so on. Okay, so if I were to then take psi star psi, where I'm wanting to know what is the probability of my momentum. Now, this is not the probability I have this momentum. I just want to know that I have what's the probability distribution of my momentum. That's a better way to say it. The probability distribution of my momentum. So I would take psi star psi dx for one dimension. And that means that I would have each of these as psi 1 plus psi 2 plus psi 3 and so on, star with psi 1 plus psi 2 plus psi 3 and so on, dx. Okay, now this and this, psi 1 and psi 2, are different eigenfunctions of the momentum. Okay, so when the momentum is measured, so when P is measured, a single eigenfunction, or I should say a single observation, of one of the values corresponding to psi will be found. So when P is measured, so when the momentum is measured, a single observation or one of the values of the corresponding psi will be found. So you've probably heard the term collapsing the wave function. This is it. So before a measurement occurs, you're going to have a superposition of all possible combinations of all of the different wave functions. Upon the measurement, which means you have psi star psi, what is the probability? So when you ask it, hey, what's your momentum? There's going to be a probability that this is an outcome. Upon a single ask, a single observation, you're going to have only one of the values corresponding to one of the wave functions. So it might be that this wave function is the one that you're then going to measure. All of the others, their psi star psi's go to 0, and you're just left with this one. So the outcome of a measurement is unpredictable. The probability of measuring a particular value in a series is proportional to the coefficient, and I've left off some coefficients and so on. But we'll get into what those are. I'm just really talking kind of superficially about superposition. So the outcome of any measurement is going to be yielding of the coefficient. But what's the key thing to keep in mind is that there's a continuous, or there is a, not a continuous, a combination of wave functions representing a particular state. And that collapses, or a single observation yields just one of them in the measurement. Okay, so this leads us to, well, what if you take so it's a single measurement. What if you take multiple measurements? We don't take single measurements. A single measurement would be a specific quantum state. You got this atom right there, like that one right there. You can see an oxygen right here. And you ask its one electron what it's doing. That would be a single measurement. We don't do that. Humans, we interact with bulk, molar quantity, 6 times 10 to the 23rd, a lot of numbers. So when you take a lot of measurements, that's where you get what's called the expectation value. Okay, and that's what we're going to do next. So this is a single measurement, and this is a theoretical idea. Okay, theoretical idea. Okay, so now to the expectation value. So this is if you take multiple ideas, the act of the measurement itself selects that one wave function, and that's when you collapse the wave function. If you do that enough times, you're then going to get the expected value of an outcome, or the reproducible outcome. Okay, And this is not the same as taking a measurement and getting a standard deviation. It's slightly different. But the expectation value is from a large number of outcomes of an observable. So the expectation value, so if A equals our observable, and I could say, let's look at the momentum, which is equal to minus IH bar d dx. Okay. So my expectation value, my expectation value is the observable or the operator. So I should say it's A is not the observable, it's the operator that's related to the observable. The observable would be the momentum. P hat is the operator related to the momentum. Okay. Expectation value, and this is only valid for a normalized wave function. So what I'm going to do is I'm going to say this equals integral psi star A hat psi dx. So you're going to have A hat operate on psi, and then you're going to multiply it by psi, and then you're going to take the integral, and that's going to give you the expectation value. Okay, so here's our example. So we've got, let's say P hat is equal to integral from minus infinity to infinity. So I'm doing this over all space. Psi P hat psi dx. This equals minus infinity to infinity. Psi minus IH bar, d dx psi dx. And let's see. So who do I have? Oh, so my psi x is for the harmonic oscillator. That's cool. So I've got a e to the minus x squared over a squared. That's cool. So if I do this, so if I put this into here, I get integral is equal to, so the expectation value is the integral psi p hat time. So this is going to be minus IH bar d dx on psi. I put this function in for psi, and then I get a e to the minus, that makes no sense. I'm going to go with it. A e to the minus x squared over 2a squared. Is that true? I just get it back again? Oh yeah, that makes sense. Harmonic oscillator. Oh, go team. Okay. So if I do this, so for the momentum, I have this function. If I do this for the position, this is kind of cool. So I get integral psi x hat psi dx. So that's going to equal, sorry, the cat is right at my feet. Hang on. Okay, I'm going to move up here to the top. So sorry about that. Hopefully you're following me. If not, watch the video again. Okay, so the position operator, I'm going to now put in my a e to the minus x squared over a squared into my expectation value here, and I'm going to get a e to the minus x squared over a squared times x, a e to the minus x squared over a squared dx. And what's cool about that is if I do this, I get equals a squared integral minus infinity to infinity e to the minus x squared over a squared. And I believe there's a 2 in front because I've got 2 of them, x dx. This equals 0 for an odd function integrated over the limits. And so that means that I have my expectation value equals 0 for the harmonic oscillator, but non-zero for the momentum. You're like, Allison, I don't follow you. That's okay, again. So this is brand new mathematics, most likely for you. It was for me too when I first started. Okay, so what have we done? We found the expectation value. What does the expectation value mean? It means when I take a lot of measurements, here's my harmonic oscillator, here's my energy, here's my position, on average, the expectation value, if I ask any arbitrary psi, hey, wave function, who happens to represent the harmonic oscillator, what is your position? It will tell you on average its position is 0 because it has equal likelihood for being this way, or for being in terms of its position. Okay. Now, if I were to ask its momentum, what's on average your momentum? On average, its momentum is going to be either so it's either moving this direction or moving this direction. Again, I'm kind of taking this as a classical harmonic oscillator, but you're going to have it's going to have a momentum either towards the center or away from the center in terms of that harmonic oscillation or in terms of that vibration. And so on average, it's going to have something. It has 0 momentum only at the center and only at the very outside when it stops. Actually, only out the outside when it stops. It still has momentum on the inside. So as it expands out, it stops and it comes back. No, that's right. And then when it comes back together, then it's going to stop. And then it's going to come back out and it's going to stop. Most of the time, though, it's spent with some sort of momentum. It's only a few times where it actually doesn't have momentum because it's going the other way. Whereas on average, there's going to be an equilibrium position where you're going to find it. And so it makes sense then that you're going to have 0 expectation value for position and a non-zero expectation value for momentum for the harmonic oscillator. Okay. Last but not least, so that's superposition, expectation value. Last thing. All of these are going to be practiced in your homework, which is why you have very long homeworks. I assign those with love. I promise I do. Probability does not equal expectation value. Probability is psi squared dx. This is looking at where could it be, question mark. So the probability density psi squared multiplied by the dimension, so it's probability per dimension multiplied by the dimension is where could it be. And this A is equal to psi star A hat psi dx is where is it. So where could it be? Probability. Where is it? Expectation value. Where could it be? It could be in all these places. Where is it? We have to measure. Upon measurement, we collapse the wave function, which means there was a superposition, there is no longer, and we do that for a very large number, what we call an ensemble, and we get this value. That's expectation value. Okay? Go team.